Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
I am Dr.
Assalamualaikum.
I am Dr. Agung Imaduddin, and welcome to today's webinar, Advanced Materials Research in conjunction with ISMM 2020, hosted by Research Center for Metallurgy and Materials, Indonesian Institute of Science, LIPI. This event is a series of webinars with International Seminar on Metallurgy and Materials 2020 that will be held on November 19 to 20, 2020. This year, ISMM will be held with the title of Accelerating Research and Innovation of Metallurgy and Advanced Materials for Inclusive and Sustainable Industry. Today's webinar has a topic of advanced material research and also has aimed to strengthen research collaborations, especially among Indonesian Institute of Science, Iwate University, and Indonesia University. Before we get started, I would like to go over a few items so you know how to participate in today's event. We have taken a screenshot of an example of an attendee interface. You should see something that looks like this on your presentation, listening using your computer speaker system by default. During presentation, you will have the opportunity to submit your question to speakers by typing into chat panel. In Q&A session, we will select some questions to be announced here and then to be answered by related speakers. We also will collect the questions that could not be announced here due to limited time, and they will be answered and published after this event. Okay. There's the thing you should know. When you join, be sure to click join with audio or call by device audio so that the speaker's voice is heard. We will turn off the microphone of all participants. Participants who want to submit a question to the speakers or in type list by Google Forms will be sent with a link in final session in the chat panel. Please click the link and input your name. We will only send e-certificate to those who input their names. E-certificate and speaker material will be sent by email to each attendee. And this is our today's agenda. In 9 a.m. we are starting the seminar. 9:05 we will have the Indonesian anthem, and 9:10 we will have opening speech by Director of ISMM, Professor Nurul, and 9:20 we will have the introduction of ISMM 2020 by Dr. Yusuke, and 9:30 we will have the featured speaker, Professor Nakanishi and Professor Herman, and then Dr. Budhy, and then we will go to closing. Now, before we start, we will the Indonesian anthem, the Indonesia Raya song will be played. Okay, please, Mr. Satrio, can you play the Indonesian anthem?
Indonesia tanah air
Indonesia Raya, Indonesia Raya, merdeka, merdeka. Tanahku, negeriku yang ku cinta, Indonesia Raya, merdeka, merdeka. Kita Indonesia Raya, merdeka, merdeka. Hiduplah Indonesia Raya. Thank you, Mr. Satrio. Maybe I would like to apologize for every participant that maybe the voice of Indonesia Raya song in Zoom application cannot be heard, but I heard that Indonesia Raya song is clear in YouTube. Okay, we will go to another session, opening speech by Director of RCCM, Professor Nurul Taufikur Rahman. Professor Nurul, you can start your opening speech.
Thank you, Mr. Agung. Good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you to each and every one of you for being here with us today. We are very pleased to be able to hold this event, International Online Seminar Research on Advanced Materials in conjunction with International Seminar Material and Metallurgy and Material 2002. I think this is the first time for us to conduct the online seminar, hosted by Research Center for Metallurgy and Materials, Indonesian Institute of Sciences. Now we have entered to the fifth month since the corona outbreak hit Indonesia. We hope that this outbreak will soon pass, and while implementing health protocols, we can continue to productively carry out our scientific tasks. Before we get started, I would like to express my sincere appreciation to all of you who generously help us make this event come together to become a success. Dr. Agung Imanuddin is my best friend, Mr. Satrio, Mr. Hendricks, Ms. Vinda, Mr. Harry, and others organization members, Professor Andika, I think here also, and especially to the future speakers who spared their valuable time to be our speakers here, Professor Dr. Yoshiki Nakanishi from Iwate University, Japan. Welcome, Prof. And Professor Dr. Akhmad Herman Yuwono from Indonesia University is my college and best friend also. Dr. Budhy Kurniawan also is my college from Indonesian University, and we could not have done it without you. We will introduce and describe our research center for metallurgy and materials works unit. Here we conduct research. RCMM, Research Center for Metallurgy and Material, is part of Indonesian Institute of Sciences, which are conducting metallurgical and material research. RCMM is under the Deputy of Engineering Science, IPT. We have excellent research in the field of steel, nickel processing, biocompatible superconductors, mineral extraction and corrosion, and others, many things. And this online seminar was held to establish closer cooperation between LIPI and other research institutions globally, especially for Iwate. We are very thanks. And also Indonesian University, of course, and others. In addition, this event also aimed to support and socialize the international seminar on metallurgical and materials events that we hold every year. This year, the ISMM 2020 will be held on November 19 to 20. Participants are welcome to attend this ISMM 2020 event. Professor Nakanishi, Professor Herman, Dr. Budhy are researchers who have worked closely with RCMM and our office, our research center, and it is hoped that this event can further deepen research collaboration with RCMM. In this event, we hope that especially undergraduate and graduate students can learn a lot from speakers who are expert in their field and become a trigger to become a global level researcher. Well, I don't want to take too much of your time. I need to leave some times for Dr. Nono to introduce ISMM 2020 activity. I think it's the time. And future speakers to introduce himself to all of you. I hope today will be fun and full of learning. So I very warm welcome to each of you and everyone. And thank you. Waalaikumsalam. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay. Okay. We go to the introduction of ISMM 2020 that will be delivered by Dr. Denny Sidki. Dr. Denny Sidki.
Okay, can I share my slide?
Presentation. You can start.
Welcome, Mr. Denny.
Okay. Okay, very good morning, everyone. Apologize, I ask permission, sincerely permission to introduce about the ISMM. Our very soon will be held our conference. My name is Denny. I am as a co-chair. So on behalf of the ISMM committee, I would like to introduce about our conference. As you can see from the left side, this is our poster about the ISMM conference. This unfortunately this year will be held by the virtual conference. This is the registration link and the date, as you can see from here. And this is the complete list topic that we provided in our conference. And please notice that we have three options for the publication. Not only the conference proceeding, but we also, for the selected paper, will publish on the journal. And we also have the signed photo exhibition. This is already the third, I think, about this exhibition. So if you have the beautiful picture about your materials, like from SEM, TEM, or whatever, or OM, that have such a phenomena, you can send to our with this term of condition. For sure, we have such a gift or the appreciation, yeah. And then, yeah, as we mentioned before, in our conference, some paper will be published in the AIP conference proceeding, which indexed by the Scopus. And this is, we already have contract. As you can see from here, this is signed on the June 17. And then we also have another option of the journal called Advanced in Natural Science, Nanoscience and Nanotechnology. This journal is under the Q2. And then another option is the CRC, This journal is under Elsevier. Fortunately, I'm one of the editor of this journal, so I can ask to the Elsevier have the permission to join with our conference now. So please don't hesitate to everyone to submit your paper as soon as possible. And yeah, this is the link of our conference, ISMM situs.op.lipi.go.id/ISMM 2020. And then, I'm sorry. The paper submission will be through the EDAS. Yeah, this is the price for the local and the global participant have a different price. And then this is for the general participant. If you just want to join but without send any paper to us, it also allow. And yeah, this is through EDAS. And after you click the EDAS, of course, this have the interface like this one. I think everyone is already familiar with EDAS. And yeah, this is the classification of the topic that we have. We have the broad topic in here, as you can see, from biomaterial, biocompatible advanced material and thin film, ceramic carbon materials, extractive metallurgy and mineral processing, material chemistry and electrochemistry or corrosion science, metal and alloys, nanotechnology and microreaction, polymer science engineering, surface and interface engineering. So once again, thank you very much, Pak Agung, for your allowing me to introduce about our ISMM, and please enjoy your webinar. Thank you, Pak Agung.
Yeah. Thank you, Mr. Denny. I hope the participant can understand our next event, ISMM 2020, and participate in that event. Okay, next, we will go to our main session today. Our today's speaker is Professor Yoshiki Nakanishi and Professor Herman and Dr. Budhy. They are the prominent professors and lecturers in the field of advanced material research in Japan and Indonesia. I would like to introduce our first presenter, Professor Yoshiki Nakanishi. Professor Dr. Yoshiki Nakanishi has the profile like this, and he now from 2016 to 2019 he was the associate professor on Department of Physical Science and Material Engineering, Iwate University, and from 2019 to present, he is the full professor in Department of Physical Science and Material Engineering. And this is his current research. I think I will not read down his current research. Maybe okay, Professor Nakanishi, you can start your presentation.
Okay.
Okay.
So yeah, just okay. Can I share my slide? I must choose the function.
You have.
Okay. Yeah.
Maybe you have to. You need to click the share.
Okay. Oh,
share,
yeah. I can select.
Share button.
I can select. Yeah, no problem. Okay.
Share,
maybe. Can you hear me? And
button.
can you see my slides? Okay.
Yeah.
Everybody.
Yeah, I can see your. Okay, I can see your slide now.
So can I start right now?
Yeah. Okay. Please.
Okay. So okay, I'd like to start my talk. First of all, I'd like to express my sincere gratitude to the organizer, especially Dr. Agung Imaduddin. He's my best friend, who got actually graduated from our university, and he got the PhD degree in our laboratory. So I'm very how to say, exciting to meet him again, and also very appreciate. Okay, so I'm Yoshiki Nakanishi from Graduate School of Science and Engineering, Iwate University. Okay, and also I must say it is very pity and sad not to visit your country and get together all the members there because of the coronavirus pandemic breakout. And yeah, before starting my academic research activity, I'd like to mention briefly about the background of our university and department, also our laboratory facilities. You know, we have quite different geographic location as shown here. So many things different. So this panel showed the comparison of weather, climate between your country, okay, the capital city, Jakarta, and Morioka. As you can see, the weather is quite different. In Jakarta, the maximum temperature, okay, is almost the same between Jakarta and Morioka, but lowest temperature is quite different. You know, in the winter season, sometimes we reach -5 or -6. In some cases, -10 degrees on Celsius. So it's really fearful for people living in Indonesia people, but we can enjoy the very beautiful nature in the well-defined 4 different seasons. So let's please take this photo. This is a lot of cherry blossom bloom in front of our main building of the faculty. We can enjoy in the cherry blossom in spring. In the winter season, sometimes they reach the -6 or 7 or sometimes 10 degrees. We enjoy also the beauty of nature. That means a blue sky with the sun shining and white snow. A lot of snow actually. A lot of snow we can see in the winter season in Morioka. So this panel showed a symbolic mountain, Iwate, Mount Iwate, which is 2,038 meters high, seen from the campus of our university. Actually, we have an event in our laboratory, annual event to climb up this Mount Iwate. It's also very nice, beautiful mountain. And if weather permit, we can see such a nice view from the top floor of our building. So we enjoy very nice natural environment. This is our, the panel, this is a picture of our group photo, but taken in 2018. In this year, unfortunately, we had not chance to take a group photo, but we take a photo by using Zoom, as shown here. It is really maybe become the memorial and impressive picture in the future. Not only academic activity, but also it's really important to do the physical exercise. So in a laboratory, so we have the football play almost every weekday in lunch break in order to refresh our brain and mental health, also mind, and also in order to keep a good relation among our members, it's very important. We have also the friendship game in once a year together with foreign student in our university. But unfortunately, this year will be canceled due to the coronavirus pandemic. It is really pity. Even in winter, we continue to play football in the snow, as shown here. So we enjoy the football, and also we enjoy the very beautiful nature, blue sky and the white snow. I like this color contrast which nature creates. This is a special way to play football, very unique to our region, Iwate Prefecture. Okay, so let me move on the academic topics. That is low temperature physics. There are also many students as audience, so I must start with the basis of low temperature material science. It's in general, materials has 5 main presentation. So this is one example to make a thin film in our laboratory. That is magnesium dibride, which is famous intermetallic superconductor substrated on the silicon. As you can see, this is a temperature dependence of the electric resistivity. As you can see, the resistivity decrease with upon lowering the temperature from room temperature, as shown here, indicating the metallic behavior, but a sharp drop was observed at TC, which is indicating the superconducting transition at around 36 or around that temperature. So, okay, this is one of the quantum phenomena. Quantum phenomena, and okay, so quantum phenomena, and okay, so next, can you see next page?
Yeah, yeah, I can see.
Okay, okay.
I can watching. Yeah, 17. We are watching
okay.
the 17. Okay.
17.
Yeah,
okay, okay.
This is 16.
16. Okay, this is one example, but there is a without movie, unfortunately.
Yeah.
And this is okay. Let me show you other experimental measurement system set up in our laboratory. This is a magnetic property measurement system, which enables us to measure magnetic property, examine the magnetic property. For example, we can measure magnetic susceptibility as a function of temperature, as shown here. And this system, of course, the student use by themselves. And if a student fabricate a new sample, they check by themselves its magnetic property by using this system. And we have also another system, which is physical properties measurement system in our laboratory. This system enables us to measure thermal and electric properties, such as specific heat measurement, electric resistivity measurement, and Hall effect, which can determine the number of carrier. Okay. This panel shows the instruction and practice for students, which we have annually once a year, how to use these kind of system. Because sometimes it is very dangerous because the user deal nitrogen liquid and nitrogen helium. Okay, liquid nitrogen and liquid helium, as shown later. And this one showed the helium liquefier system established in our campus, Iwate University, and also the liquid nitrogen generator. So as you can see, that we have an environment well established for low temperature material science. This picture shows okay, a refill from tank track to liquid liquid nitrogen container called evaporator. Okay, so next let me show you one demonstration using nitrogen liquid. Can I see this movie? And put oxygen gas into nitrogen liquid to make a liquid state of oxygen. Yeah, this is a very famous example for low temperature physics. It changed its physical property dramatically, as you can see. So take a look, please. This is the color of liquid oxygen, light blue, sky blue. Yeah, it's totally markedly different from those at room temperature. And surprisingly, okay, this liquid oxygen changed its magnetic property also. It becomes magnetic. So the physical property of materials changes. Its properties depend on the environment, external parameters such as temperature and pressure pressure. Okay, so let me move on other physical property, that is elastic property. This panel shows the stiffness of materials. As well known, the diamond is stiffest and the hardest material in the nature. On the other hand, one of the typical soft material is the air and the water. Okay, if materials are okay, in general, the materials become stiffer, harder on lowering the temperature when the temperature decreases. This is a normal behavior of materials. Okay, let me show you some let me show you some demonstration to present this behavior. Okay, this is okay. You know the banana. I love it. I ate in this morning. If we put the banana into liquid nitrogen, you know, this becomes very hard like this. So now we can call it banana hammer, and one can hit a nail like this, banana hammer. Okay. So again, I'd like to remind you the most of the material become stiffer, harder on lowering the temperature. So this is elastic constant and versus temperature. The behavior is like this: stiffing on lowering temperature like this. But in some special cases, it showed softening on lowering the temperature, which we can see in the case of rare earth compound that is a highly correlated electron system. So like this. So in the latter of my talk, I'd like to show this the recent result of a highly correlated electron system. To evaluate the elastic property of materials, we use ultrasound measurement because sound velocity propagating in a solid is proportional to elastic constant stiffness of materials. Exactly speaking, elastic constant is proportional to square of velocity. Okay, I don't go to the detail, but this is all experimental apparatus, equipments setting up in our laboratory. And this one showed just a toy model. The stiffness of material is like the spring constant. So when a material becomes stiff, the spring constant increases. Okay, this is also a movie, but now it doesn't work. So just skip. Okay, this is one example. Ytterbium platinum antimony. It's one of the highly correlated electron system with containing one of the rarest ytterbium. This one shows the temperature dependence of elastic constants. One mode C11. As you can see, the elastic constant decrease on lowering temperature like this. And since this system exhibits magnetic transition, so we can observe the clear step-like behavior at around 700 millikelvin. So I must say, we have dilution refrigerator. This is a special experimental apparatus, and which enable us to go to the low temperature down to 40 millikelvin. So this is the inside of the dilution refrigerator, and combined with magnetic field, we can measure. We can conduct ultrasound measurement in a field up to 10 Tesla, and in the temperature down to 40 millikelvin. Okay, so skip. And okay, I'd like to show you other ytterbium compound system. This is ytterbium so-called 1-20 system. They show also the elastic softening as shown here, like this, in the temperature dependence of elastic constant. Is in particular, in the case of ytterbium cobalt to zinc 20, we have pronounced elastic softening characteristic behavior at low temperature like this. Okay, so we observe also the other system contain the other rare elements such as praseodymium and neodymium. As you can see, the pronounced elastic softening, as shown here, highlighted here, observed in the temperature dependence of elastic constant. So, okay, this is quite different behavior compared to ordinary, normal material. Not only at low temperature, but also the other physical parameters such as pressure, we could find such kind of behavior. This is one of the recent, one of the featured topics of our research. But please take a look left panel. This is a temperature dependence of elastic constant of cerium, which is a rare cerium rhodium to silicon 2. At ambient pressure, the elastic constant keep almost constant independent of temperature, but it shows this kind of step-like anomaly due to magnetic transition to successive transition. But in application pressure, as you can see, gradually the elastic softening grow up, and at the pressure of 1 GPa, we observe the pronounced elastic softening as we see the other rare systems. So we call it pressure-induced elastic softening, which is also opposite behavior at room temperature. Okay, so time is running. So finally, I'd like to show you. This is I stopped my talk, but this is a final example which we done currently in our laboratory. But the europium, this is also the rarest europium aluminum-4 and the europium gallium-4 system. These systems show the very large elastic softening, not large, but huge, enormous elastic softening. In the case of europium gallium-4, from room temperature, it starts the softening. And okay, almost 83% elastic softening was observed in the case of europium gallium-4 in the C44. It's one of the principal mode, elastic mode, as a function of temperature. So europium gallium-4 changes its elastic property dramatically at low temperature, just like okay, and at room, okay, this europium gallium-4 at room temperature is like iron, but at low temperature, it changes dramatically its elastic property, like one of the famous sweet pudding or typical Japanese food, tofu. So it's a really wonderful and fantastic behavior at low temperature. Okay, so let me summarize my talk. I show you, introduce you our a little bit of university and department, and also our laboratory experimental facility. And also we show you the ultrasonic measurement and demonstrate that ultrasonic measurement is very sensitive to elastic property of materials of the low temperature of physics. And finally, I show you the typical example of highly correlated electron system. Although we quickly show you. Okay, so thank you so much. Thank you so much for your kind attention. Terima kasih atas perhatiannya.
Please start your presentation.
Okay. Thank you very much, Dr. Agung, for your kind introduction about me. I have sent my PowerPoint slides to Mr. Satrio, and I asked him to share the screen for me. So I think it would be more convenient because the control is done in your sides. So I just prefer that there is no delay. Okay, that's very good. Yeah. Yeah. Thank you very much for very kind invitation for me to give presentation in this nice event, the International Online Seminar, Advanced Metal Research in conjunction with ISMM 2020. So my title of presentation is Nanostructured Semiconductor Oxide Materials based on indigenous local resources. My name is Akhmad Herman Yuwono, and this work has been done with my team, including previously my PhD students, Dr. Amalia Soleha. Now she's in Department of Metallurgical Engineering, University of Sultan Ageng Tirtayasa as the lecturer, and also Dr. Latifah Hanum Lalasari, one of the Research Center for Metallurgy and Material staff, the researcher over there. And also this work has been done together with my colleagues, Dr. Alfian Ferdiansyah, Dr. Donanta Daneswara, and Dr. Nofrijan Sofyan. Okay, next slide, please. Yeah, I think Dr. Agung has introduced me already. So this is my profile. Maybe if some of you want to contact me, so you can email or send me through WhatsApp message. Okay, next, please. Next slide, please. Yeah, so because today's event is in conjunction with ISMM 2020 So I noticed the theme of the ISMM 2020 is the accelerating research and innovation on metallurgy and advanced materials for inclusive and sustainable industry. So I have noted two keywords for this event here as the part of the ISMM 2020 is advanced material research and sustainable. So these two key, actually the spirit of our today's discussion and sharing, as well as my presentation. So please, next slide, yeah. Next slide, please, yeah. Yes, I think many of us already know about the advanced materials, but let me refresh our understanding about the advanced material. I put some definition from several websites. So for example, advanced material are materials with engineered properties created through the development of specialized process and synthesis technology. So this is the keyword, specialized process and synthesis technology. Advanced material can also be defined as those exhibit greater strength, higher strength, density ratios, greater hardness, and one or more superior thermal, electrical, optical, or chemical properties when compared with traditional materials and with properties needed to perform a specific function and often entirely new function. So this is the keyword, to perform specific function and often entirely new function. Advanced material can also be defined as any new or significantly improved materials that provides a distinct advantage in physical or functional performance when compared to conventional materials. Next slide, please. And I think the last materials, the advanced material can be defined as those are utilized in high technology application. These examples are electronic equipments, computers, fiber optic system, spacecraft, aircraft, and military rocketry. The advanced material also, those are used for high-tech. This can be a device or product that operates or function using relatively intricate and sophisticated principles. Or they might be of material, previous slide please, whose properties have been enhanced or newly developed. So these are all application of the advanced material, although maybe it is not limited. There are some other application. For example, we know that for advanced material in energy application, there are a lot of examples for dye-sensitive solar cell, battery, and also for transportation. For example, the airplane fuselage is made of a very advanced light material. Environment, for example, desalination system or the pollutant degradation. For health or medical application, they can be used for drug delivery system or prosthesis material. For construction, the engineered wood or the advanced concrete. In ICT, at nowadays that we cannot avoid that every day we use cell phone, yeah, and all of the components are made of the advanced material. Remember also defense or security, for example, armor or night vision or missile material, very strategic in defense and security application. And of course, there are some other application, for example, smart clothing, packaging, agriculture, and many applications of advanced material. They are very intricate principle that must be applied by using the advanced material. Next slide, please. And as the materials community, we know that the history of mankind is story of materials, isn't it? Yeah. That the development of the culture for human being all over the world depend on the materials developed by the society. So if we look at the history that from Stone Age, Bronze Age, Iron Age, until now the Information Age, that these are all related to the development of materials. So since the beginning of the human civilization, that people use the natural materials directly from the nature. So the natural material can be defined as those extracted directly by human being from the nature. So they use it directly. So there is no such improvement or something like, for example, the woods, the stone, yeah, long time ago, our ancestor took it from the nature and use it for their daily life application. And the materials with the advancement of the the human civilization, so it goes to engineering materials. We know that engineering material, of course, we are very familiar with the the tetrahedron of the material: structure, processing, properties, characterization, and performance. So these are always our mindset when we think about the engineering materials, the materials that are improve the properties by using this kind of thing. And finally, as I already mentioned in the previous slide, the advanced material goes with the new sophisticated application. Is it? Course, as our obligatory, by the United Nations, that all of effort must be intended in order to support 7 goals to transform our world. Sustainable development, for example, we should attain and achieve no poverty all over the world, and zero hunger, good health and well-being, quality education, gender equality, and so on, until all the 7 sustainable development goals target can be achieved with our efforts. So in this sense, we are, as the materials community, we always think that how we can use our materials expertise in order to support the sustainable development goals. So that's why my title is trying to relate the natural resources as part of how we can use this for many application stated by the sustainable goals. Maybe some of the target are not very related to us, but more or less, as I mentioned previously, that the human mankind, the population are always related to the development of material. So there must be a need of the material for supporting the society. Okay, next slide, please. Next slide, please. Yeah, this is some critical issues that we are facing in our daily life as the urban society. So why I put emphasis of urban society? What about the rural or our brother and sister living in rural areas, in the remote areas? This is also part of our concern here as the nation. Yeah, because I see that in the participant list that many of us, coming from Indonesia, so I just try to give awareness for at least myself and for all of you of the audience, that we have to concern about our nation's problem. For example, the urban society, because I'm quite sure that many of us or most of us living in the cities, that urban society always have this kind of problem. For example, declination of fossil fuels, waste, pollution, clear water and air, and transportation. This is actually what we are facing everyday life. Yeah, so that's why as the materials community with our expertise, we are trying to use our expertise to solve the problem with this kind of things. Next slide, please. Next slide, please. Yeah. Regarding the declination of the fossil fuels, the energy coming from oil and gas, that we realize that the sources will be very reduced in a very short time, maybe in another few years. Then we are concerned about the renewable energy. One of the resources for renewable energy is the dye-sensitized solar cell. I think many of us already know about this. Maybe I don't need to explain about the principle of the DSSC or dye-sensitized solar cell, but I'm trying to mention about some governing factors. What factors are important to improve the dye-sensitized solar cell? First, important factor is the suitable nanostructured semiconductor oxide. And second one is development of sensitizing dye and electrolyte. And the third one is new alternative counter electrode. More specifically, with the nanostructure semiconductor oxide, as I put in my title also for this presentation, that the preferred nanostructure semiconductor oxide must have high surface area, because this is intended to give intensive interaction with the dyes, the sensitizing dye molecule. So that's why it can absorb more photon energy from the sunlight. And the second concern with the nanostructure semiconductor oxide, that it should enable the photon energy absorption can happen in the visible light spectrum. So that's why in order to observe the photon energy, of course, the highest intensity is the UV area. But of course, we don't want that our solar cell, our dye synthesis solar cell, can only work in the UV area. So we want that even in the visible light spectrum, that our densitized solar cell can work properly. So this is the concern regarding the nanostructure semiconductor oxide, the high surface area and the photon energy in the visible light spectrum. So how we can engineer our nanostructure materials in order to provide this kind of two things here. Next slide, please. Yes, I think many of us already very familiar with this simple schematic. Yeah, this is the schematic, which is too simple, I think, for physicists such as Professor Nakanishi or Dr. Budhy Kurniawan, or maybe some of you whose background are physics, field. Yeah, but I think what I present here is in order to refresh again our basic understanding about the band gap energy, because I think the nanostructure material, more specifically the semiconductor material, are always related to the band gap energy. So, for example, the insulator are considered as the material whose band gap energy are very large. So that's why the electron in the valence band cannot excite to the conduction band easily, unless there is a very high energy that can excite the electron from the ground state to the excited state. What about the conductor? As we know, the example of the conductor, of course, is metallic material. So the position of the valence band and the conduction band are even overlapped. So that's why the electron maybe can swim or can fly freely from valence band and conduction. That's why in terms of the electrical and thermal conductivity, the metallic material are the best one, because there is no such band gap energy over there. What about the semiconductor? The semiconductor are in between the two characteristics. Yeah, that's why it still has the band gap energy, but the value is not as large as the insulator material, although it is also not overlap between the valence band and conduction band, but there is still band gap energy with the semiconductor material. So I think this is the main important thing, that our basic understanding about the semiconductor materials. Yeah. Why we are concerned about the band gap energy material? Because we can engineer, or we can modify the application using the semiconductor material by engineering or by modifying the band gap energy. For example, the photocatalytic mechanisms in order to degrade the pollutant from the, for example, the liquid medium. Of course, the band gap energy is the very important key in order how the materials can absorb the photon energy to activate the electron and hole formation. Next slide, please. Yes, I think this is some example how we can modify the band gap energy. That's why the modification of the band gap energy by using several ways is called as the band gap engineering. So the engineering how to modify the band gap, it can be defined as the process of controlling or altering the band gap of a material. Yeah. This is typically done to semiconductor by controlling the composition or allowing or constructing layer material with alternating composition, or we can also modify the nanostructure size, the crystallized size of the nanostructure material. So this can be done in order to change the band gap energy value. Next slide, please. Yeah, I think many of us studying about the nanotechnology are very familiar with this figure. Yeah, we have several bottle containing semiconductor material. For example, this is the indium selenide. Yeah, yeah, with different composition. The previous slide, please. Yeah, no, previous slide. I haven't finished this one, please. Yeah, so we are familiar how in the change, the color change can be done by adjusting the composition of the components here. Yeah, for example, this example is the indium selenide, yeah, with the stoichiometry of the indium and selenide with different compositions, so we can adjust the color. I think some of us are thinking about, oh, why color? Yeah, color is actually the representation of about how the material can respond to the photon energy absorption. So this is one of important basic about the semiconductor material for being used in the device. Another example also, for example, this the zinc oxide with the woodside structure. Yeah, we can also enhance or maybe enlarge the band gap energy of the zinc oxide by making the zinc oxide in the nanoporous form. Yeah. Next slide, please. Next slide. Yes, please. Yeah. So this is the semiconductor behavior. I think all of you are familiar with the, the left-hand sides. Illustration, the conduction band and valence band. So if there is a photon energy coming, the electron can be excited by absorbing the energy to conduction band. Yeah. So it can be the conducting material while they are in the conduction band, and after several maybe time, yes, and then they can go back to the valence band. So this is the basic understanding about the semiconductor behavior. Yeah, if there is a photon coming, so it can be absorbed by the electron, to get the energy to be excited. So one important thing actually is the semiconductor material can only excite its electron if the photon energy is at least the same as the band gap energy, the intrinsic band gap energy, or more than that. Yeah. If the photon energy is less than the band gap energy, there is no way that the semiconductor material want to absorb the energy. So maybe some of you, because I see that in the participant list that many of you are Indonesian also, and maybe some of you are also from the same period of me last time. Maybe you can see that this funny figure. Yeah, maybe some of you know this figure, Pak Oga. Yeah, Pak Oga is. So I always give this example in my class in order to make the understanding about the semiconductor material much easier. Yeah. So Pak Oga, if we remember in Unyil session that he always asks the Unyil to give him cepet. Cepet means actually 100 rupiah. Professor Nakanishi, I'm sorry that I give maybe the example in Indonesians, cartoon here. I think it is much easier for us to understand the behavior of semiconductor material in terms of Pak Oga behavior. So he always asks cepet. Cepet means actually 100 rupiah to Unyil. So because Unyil doesn't have 100 rupiah, he just want to give 50 rupiah, 150. Yeah. So cepet, maybe 100 rupiah is nothing at the moment. Yeah. But in my age last time, cepet is was still worth it to buy something. Yeah. Some food. Yeah. So because Unyil can only give 50 rupiah, so he just say, Pak Oga, I don't have 100 rupiah. I give you 50 rupiah. You want it? And Pak Oga said, no, I don't want it. I want 100 rupiah. I don't want 50 rupiah. If we think that Pak Oga is smart enough, actually he can ask 50 rupiah from Unyil, and another 50 rupiah from your friends, for example, Usro, Mei, Lani, on Usro, Utrit, and so on. But Pak Ogah doesn't want to do that. Once he wants 100 rupiah, he always asks full 100 rupiah, not 50 rupiah plus 50 rupiah. So the behavior of Pak Ogah in this sense is totally the same as semiconductor material. So by understanding this one, so we can understand why the glass materials is transparent, because it doesn't absorb the photon energy from the sunlight. So that's why it goes, or if it transmits the light, it transmits without any observation, because the glass material is amorphous material. It, of course, if it has band gap energy, it is very large band gap energy. So that's why it's always transmitting the photon. So this is actually the very simple and basic understanding about semiconductor matter, but it is very useful while when we want to understand about the band gap and band gap engineering. So this is another example. Maybe the previous, yeah, the figure at the bottom. So we can see that one person is begging for his Lexus car to be tuned up. So we can imagine that for the Lexus car, as considered as the luxurious car, needs tuned up, and the person is begging to anybody passing through him. Yeah. So this is actually also representing how the semiconductor materials. So the semiconductor materials can be said as the dignified beggar, or arrogant beggar. So they want to get photon energy at least the same as their band gap energy. So it is, if it is less than that, then there is no way they want to absorb it. Okay, continue, please. Yeah, regarding the dye-sensitive solar cell, of course, people think how to improve the efficiency. So that's why people think how to use one-dimension nanostructured materials, for example, zinc oxide nanorods or titanium oxide nanotube, in order to give expected ballistic effect of electron transfer. So if the nanostructure semiconductor oxide in the dye-sensitive solar cell is in the form spherical, so the electron transfer or electron trajectory still in the diffusive way. So they are still scattering here and there. By using the nano tubes or nano rods as a kind of the hollow or one-dimension material, so the electron transfer can be expected to move in the ballistic way. Yeah, so the velocity can be expected to be much faster. That's why in the dye-sensitive solar cell, the use of zinc oxide nanorod or titanium oxide nanotube are expected to provide this kind of things. Yes. My previous PhD student, Dr. Amalia Soleha, now she is already back in her university, Sultan Ageng Tirtayasa. Last time she worked very intensively to make the zinc oxide nanorod. Continue, please. Next slide. Regarding the titanium oxide nanotube, of course, we can use the nanoparticles, TiO2 nanoparticle, which is commercially available in order to provide nanotube. So the technique is adopted from Kasuga works. I think this is a very famous works in order to synthesize TiO2 nanotubes by a very simple process, the hydrothermal process. So the TiO2 nanoparticle, is immersed in the sodium hydroxide solution in an autoclave. Then during the application of high pressure vapor at certain temperature and certain pressure, it will provide nanoseeds. And during the rinsing or cleansing of the nanotube by using the water in order to get the natural pH, so the nanoseed will wrap up to provide nanotubes. So this is very simple process, but we can use it in order to provide nanochips. Of course, the TiO2 nanochip can be also synthesized by using anodization process or some other, physical process. Yeah, this TiO2 nanochip, of course, very useful for dye-sensitive solar cell and also to provide hydrogen evolution, pollutant degradation, and selective oxidations. But something that we have to remember that the result of the hydrothermal process of TiO2 nanoparticle immersed in sodium hydroxide alkaline solution, that the nanotube is still in the form of amorphous sodium titanate. So because it was mixed and immersed in sodium hydroxide, a very strong alkaline solution, of course, the resulting nanotube still in the form of amorphous sodium titanate. There is still element of sodium in the nanotube. So it is not purely titanium oxide nanotube yet. That's why based on the TM image, we can see that there is no such indication that it is crystalline materials. What should we do? We have to, to enhance the crystallinity of TiO2 and to get rid of the sodium element from the nanotube by using the conventional annealing process. Yeah, this is the X-ray diffraction result. A, B, C, D is the A sample is the nanotube after the hydrothermal process. I think this is still amorphous, as we can see that this is the indexing show that this is still amorphous sodium titanate. And when we subject this nanotube to conventional annealing, or can say calcination, at 300, 450, and 600 degrees Celsius for 24 hours, then we can see that the diffraction peak of the anatase and rutile appear here, and the peak of the sodium titanate in B, C, and D has can be considered gone already. So by improving the calcination or annealing temperature from 300 degrees Celsius to 600 degrees Celsius, then we can find the anatase and rutile crystalline phase of the titanium oxide. So we can consider that in terms of the crystallinity, it is successful. But based on the SEM image, the next slide, please. Next slide, please. Yes, this is the scanning electron microscopy image with A is the TiO2 P25 degussa as the initial powder. Yeah, we can see that there are some small nanoparticles within this big aggregate. So that is very normal with the nanoparticle if they are gathered and they make the such kind of aggregate like this. But we can still see that there are some small nanoparticles within this aggregate. And the B is the sample after the hydrothermal process, yeah, dried at 100 degrees Celsius. For the B image is the result of the amorphous sodium titanate. So we can see that the nanotube has been resulted, yeah, successfully, yeah. But according to the X-ray diffraction result, that they are still amorphous sodium titanate. They are not TiO2 crystalline phase yet. But when we improve the crystallinity by subject them to calcination, C, D, and E, then we can see that the nanostructure has been collapsed already. Then you can see that at 300 degrees Celsius, the nanotubes, yeah, just like the wiring form, are still observed, but many of the tubes has been collapsed here in order to form such kind of aggregation. And at higher temperature at 450 degrees Celsius and 600 degrees Celsius, the nanotube structure has been totally collapsed. Yeah. But according to the X-ray diffraction, of course, we can estimate the crystallite size of the anatase by using the Shearer's formula. For the TiO2 P25 degussa, of course, the crystallite size is quite large because it is the original one. And as dried nanotube, the crystallite size of anatase is only 5 nanometer. Yeah, it is expected because the phase is still amorphous and the anatase phase is still very little. Yeah, that's why the crystallite size is only 5 nanometer. And when we improve the crystallinity by calcination at 300 degrees Celsius, the crystallite size has been improved to about maybe 9 or 10 nanometer, and improving the calcination temperature further to 400 degrees Celsius and 600 degrees Celsius, and the crystallite size has been significantly improved. But again, the growing of the crystallite size, of course, has made the structure become collapse. Yeah, that's actually the challenge that we have by using the conventional calcination or annealing. Next slide, please. Then we are trying to think about how we can improve the nanotube's crystallinity, but at the same time, we have to maintain the hollow structure. If we did the calcination, of course, the crystal size can grow significantly, but at the same time, the nanotube will be collapsed. That's why we think about one way in order to improve the crystallinity of nanotube and maintaining the hollow structure by using the post-hydrothermal treatment. So previously it was hydrothermal treatment, and this stage is called post-hydrothermal treatment. Actually, this is the same as what we do every day in our life. Yeah, this is the rice steaming philosophy. We use for example, dandang in bahasa Indonesia in order to make the rice that has been boiled, to provide more well-cooked rice. Yeah, actually we do it by using the same philosophy, rice steaming philosophy. Of course, we put our sample by using a special fixture in this autoclave, and let the water vapor to do its duty to improve the crystallinity of the material. So this is the TM image of the nanotube. Hello. Yeah. Actually,
Herman,
before
Professor Herman.
Yeah. Hello. Can I continue?
Yes, please, Professor
Can I
Herman.
continue? Yeah. Okay.
Yes,
then
of course.
We can see that from the TM image that the sample after pre-annealing at 150 degrees Celsius follow with post-hydrothermal treatment. Yeah. So this is the example that before we subject the nanotubes to the post-hydrothermal treatment, we need to do pre-annealing at 100 degrees Celsius. Why? Because we realize that the high pressure of the water vapor during the autoclave post-hydrothermal treatment can make the structure collapse. That's why we try to give a pre-annealing treatment at 100 degrees Celsius by using a conventional furnace, then followed by post-hydrothermal treatment. That's why we can see that by applying this kind of thing, the crystallinity of the nanotube has been increased. We can see that there are some small crystallite protruding out from the nanotube structure. This is the indication that the crystallite size of the nanotubes can grow further. Yeah, but at the same time, the nanotube structure can be maintained here. Yeah. Next slide, please. Yeah, this is the result of the X-ray diffraction. We can see here that with A is the nanotube that has been subjected to 80 degrees Celsius, and B for 100 degrees, C 120, and D 150. But remember that before we subject, previously, please, I haven't finished. Yes, yeah. Before we subject to post-hydrothermal treatment, we have done the pre-annealing at 100 degrees Celsius, 150 degrees Celsius for 6 hours as a kind of, making the nanotube can be strong enough before being attacked by the water pressure at high pressure. We can see that here the crystalline size can improve, although maybe it is not as large as with the result of the conventional annealing, but the improvement is quite, satisfying. And also we can see that the band gap energy. So now we are concerning about the band gap energy. So the band gap energy with the sample at 80 degrees Celsius post-hydrothermal treatment is still 3.75. So the bandgap energy was obtained by using the UV spectroscopy, and we used the tau equation in order to estimate the bandgap energy. So we can see here that by increasing the crystallite size of the anatase phase in the nanotubes from 7 nanometer to about 8 nanometer, that the bandgap energy decreased from 3.75 to 3.67. So it is quite promising that by increasing the crystallinity or the crystalline size, then we can adjust the bandgap energy. Next slide, please. Yeah, and then yeah, this one. Yeah. So further, we try to modify the pre-annealing temperature. Previously, we subjected to pre-annealing temperature at 150 degrees Celsius, but now we enhance to 300 degrees Celsius. That we can see that the result is quite more promising, that the bandgap energy value at post-hydrothermal treatment at 100 degrees Celsius or 120 and 150. So the bandgap energy can be reduced further to 3.39 or until finally it's 3.23. So it's getting closer to the bandgap energy of the inherent properties of anatase, which is 3.2. So that's why we can see from the TM image that by increasing the post-hydrothermal treatment, but previously we used the pre-annealing temperature, so the nanostructure of the tube can be maintained. So we can see here that the nanotube, is very smooth, and inside the tube there is much more. Black. Structure. This is actually the indication of the crystalline anatase. So by using the selected area diffraction, of course, we can also see that there are some dots showing that actually the crystallinity is improved significantly. Okay. Yeah, we use it these nanotubes for our dye sensitive solar cell maybe, but I'm not showing you in this presentation. And last time we can see that actually the efficiency of the nanotube, the DSSC made by this nanotube has been improved. Of course, the efficiency is not as high in the silicon based solar cells. So this is actually still always the problem and challenge with the dye sensitive solar cell. The efficiency is still quite considered low. But why I'm showing this example for dye sensitive solar cell, although maybe now at the moment the perovskite solar cell is more promising, but at least we can see that the nanotubes can be made by our own local resources. That's actually the main message. For the next slide, please. Yeah. Next slide, please. Yeah. So actually, this is the mechanism why the crystalline enhancement by using the post-hydrothermal treatment, because previously by using the sol gel method, actually we can always have this amorphous material, but by using the post-hydrothermal treatment, actually we can rearrange the flexible TiO2 bonds in order to get more densified nanocrystalline TiO2. So this is actually the secret behind the crystallinity enhancement by post-hydrothermal treatment. Next slide, please. Yeah, this is also confirmed by FTIR by increasing the pre-annealing temperature before subjecting to post-hydrothermal treatment. Actually, we can provide more TiO2I nuclei to be rearranged during the post-hydrothermal treatment. By using the FTIR spectroscopy, we can confirm this one. Yeah. Next slide, please. Yes, I think now the next slide is more on motivating all of us in Indonesia. We realize that our country is very rich with the resources, and we have a lot of islands. I think Prof. Nakanishi should come here, to visit Indonesia. But maybe hopefully the COVID-19 will be finishing soon in Indonesia, then we can do some visit also. Yeah. Okay, this is a very beautiful island. I think many of us know about this, Raja Ampat, Bali, Bunak, and so on. Yeah, we have a lot of beautiful areas in Indonesia. But remember that actually, besides the beauty of the country, that actually we also have the abundant local resources that can be used to provide the nanostructured semiconductor oxides. Yeah. Next slide, please. Yeah, I think some of you are from the Bangka Belitung Islands, so I really, appreciate that people over there also have this very, potential islands. Yeah, besides the beauty of the Bangka Belitung Islands, so we know also that Timah, as one of the BUMN in Indonesia, has provided the Timah ingot, with as one of our Indonesia second devisa on top of the country. Yeah, so the Timah in Bangka and Belitung has provided this very worth and rich devisa for the country. But remember, actually, besides the tin itself as the metal, that we have some other mineral that needs to be optimized and to be used as the semiconductor materials. Next slide, please. Next slide, yes, please. Yeah. Yeah, I think this work, previously, yeah, this work has been done by the Research Center for Metallurgy and Materials, LIPI, already. Yeah, how to extract the ilmenite, the byproduct of the tin mining is the ilmenite, Fa2O3, TiO2, yeah, by using several methods, hydrothermal method or pyrometallurgy, yeah. So it can be extracted in order to provide titanium oxosulfate as the precursor for making TiO2 nanoparticles. So this work last time was done by my previous PhD student, Dr. Latifa Hanum Larasari. Now she's the very active researcher in Research Center for Metal and Materials, Dr. Agung's colleagues. Yeah. So last time, this work has been obtained already. How we can extract the ilmenite, yeah, Fa2O3, TiO2, in order to form TiO2 nanoparticle. I think the distribution of the site is quite uniform. Yeah. And actually, there is one promising improvement. Then, besides the nanoparticle in the spherical form itself, then we can find this kind of thing, the nanotubes. So this is one fact that actually we can provide the TiO2 nanotubes from our own local mineral. Why I emphasize this one? Because if we only use the commercial available provided by overseas manufacturer, for example, TiO2, the well-known resources is TiO2 P25 Degussa. It is made by Degussa GmbH company in German. Then if we always use this one, we always depend on the resources from the overseas. Yeah. So there is no way that we can catch up the advancement in the developed countries. For example, we want to synthesize one material, but actually they are already 5 or 6 steps ahead in front of us. So that's why the strength of the Indonesia development of the nanostructure as part of the advanced material is when we can use our own local resources, because we have the abundance local resources. Then the challenge is how to convert them into the material that we need for sophisticated application. I think for the TiO2, besides using in DI, sensitized solar cell or photocatalysis, TiO2 also used for many industry, for example, painting industry, pigment, and some other. And also, for example, the sensor. Many of the sensor material are made of the perovskite. Perovskite structure. Yeah. Then that's why TiO2 is always needed. Yeah. TiO2, titanium oxide. Titan is the name of the giant in Greek word, so that's why it gives the giant effect on many applications. Next slide, please. Yeah, I think this is the last slide that I present today. It is not, conclusion, but I just give you, and at least for myself, that we have this kind of potential to be developed further. So we can produce TiO2 nanoparticle on even larger scale from ilmenite, because in the previous work, then we can only get a small amount of TiO2 nanoparticles, from the ilmenite. If we can, if we can scale up, the line of the production, then we can provide TiO2 nanoparticle with uniform distribution in particle size. And also, previously, we can see that in order to purify the TiO2 from the ilmenite, of course, the iron element is considered as impurity. That's why we are trying to improve the purity of TiO2 by removing the iron element. But in fact, actually, the iron element in the TiO2 can be considered as element that can modify the band gap energy of the material. So that's why maybe we don't need to remove out the element iron element from the TiO2 nanoparticle, but it can be considered as the doping, to modify the band gap energy. Maybe we can find any application that can be used the Fa2O3 TiO2, where the iron element is still considered as the impurity that can modify the band gap energy. And again, the conversion of local source derived TiO2 nanoparticle from ilmenite can be converted to nanotubes. Previously that we still have very small areas in the TEM image showing that TiO2 nanotube has been formed. Now we are trying the collaboration between Department of Metallurgical and Materials Engineering, Universitas Indonesia, and the Research Center for Material and Materials, try to improve and to optimize the synthesizing parameters in order to get more nanotubes. And another nanostructure material that can be developed further, for example, for photocatalysis to degrade the pollutant from the liquid environment. Remember that the thin materials, the thin metal that has been extracted from the Bangka and Belitung mining, the SnO2 is also very potential, especially in the form of nanostructure. So if we can make it as the nanoparticle, nanotube, or some other nanostructure, of course, the use for photocatalysis and also maybe some dye-sensitive solar cell can be enhanced by this one thing. Another thing, actually, this is related to the synthesis of nanohybrid or nanocomposite. Last time in my previous work during my PhD in NUS, then the TiO2 combined with the polymer, polymethyl methacrylate, nanocomposite thin film can show third order nonlinearity with a very high Chi3 value. So this can be done, this can be achieved when the inorganic nanostructure material is encapsulated by the polymer matrix. When we increase the crystallinity of the TiO2, then maintaining the polymer materials are still in a good condition, then we can get the very high intensity in terms of the response to the laser simulation. We can get the third order Chi3 value. We can do this also if we can find a way how to embed the TiO2 from ilmenite Bangka Islands resources, or SnO2, the thin oxide asset, in this kind of nanohybrid or nanocomposite thin film, then definitely we can maybe use it for optical grading. And the last one actually is when we think about the arrangement of the nanoparticle, we can apply the self-assembly technique by using the surfactant or double coupler templating. So that's why we can use this approach as the bottom-up approach in order to arrange the position of the nanoparticle, for example, TiO2 or SnO2, by using the local plantation or seashell. Remember that God has given us a very, blessing, very abundant blessing with our local plantation. Actually, with we can see that in the local plantation, anything that there are actually many porous form in our local plantation. Actually, it can be used as the templating in order to arrange the nanoparticle formation. And we can also use the seashell, because once while we can see the cross section of the seashell, actually the porous structure are very well arranged and very beautiful. God has given us this kind of thing, and it depends on the way how we can modify this in order to provide materials that support our human life, and also to conserve our environmental. So this is, I think, my message is in order to connect the advanced material and the sustainability, and how we can conserve our environment in our life with a very wise way. Yeah. I think that's all my presentation. Yeah. Thank you very much for your kind attention. Yeah. Thank you.
Thank you. Thank you, Professor Herman.
Thank you, Prof.
For your
Herman.
interesting
Welcome. Yeah.
Thank you for your interesting topic for
I
For
have
the
the
second. Yeah, okay, thank you. Yeah. As introduction in this presentation, I would like to explain about the characteristic of our sample. In this sample, there are some several unique physical properties. For example, magnetocaloric effect, yeah, and then magnetoresistance phenomena, and also some of the exploration by electron spin resonance. This material can be used, for the example, for the active magnetic refrigerant, yeah, and also for the spintronic devices, yeah, hard drives, read write head, and magnetic sensors, and also for the heterojunction in transistor. But in this presentation, I would like to give my emphasis to the first condition, magnetocaloric effect. From this curve, we see that the minus delta entropy is the main thing that characterize the sample for the magnetocaloric effect. In this sample, in this slide, we see that the value, the value of the minus delta entropy is about 5, in this sample. So we want to explore our sample in this basis. And the evolution of the studied sample, we have a history of the sample. Since in our sample, we have some of the derivative of the sample. First, as the parental compound is LMO, lanthanum mangan oxide. It is a perovskite lanthanum manganite, and we modify this sample with partial substitution at A sites. It means at the lanthanum site, with two kind divalent ion substitution or monovalent ion substitution. For the divalent ion substitution, we see that lanthanum doped by barium, calcium, or strontium. For the monovalent ion substitution, lanthanum is doped by natrium, potassium, and silver. And also we can mix by divalent and monovalent ion substitution. Next, please. So for the our sample, our sample is based on the LBSMO, lanthanum, barium, strontium, mangan oxide. If we see from this sample in the figure, minus delta SM atau minus delta entropy, for the LBSMO, we have the highest value of minus delta entropy is about 2.3, for the minus delta SM. And also, we found that in this sample, for the magnetoresistant phenomena, there is also the low field magnetoresistant phenomena. So this kind of the unique characteristic of the sample that give our intention to develop and to explore some of the physical properties in this material. Next, please. So in this material, we try to substitute potassium as the monovalent ions for the sample. In the figure, we have some of the many of the monovalent ions, natrium, silver, potassium, and we see in the curve of minus delta entropy, the highest value of the some kind of substitution is produced from the potassium substitution in this sample. And also, some of the researcher also find these properties. So based on this information, we try to make substitution, potassium substitution in our sample. Next, please. What is the novelty of our research here? First, system with the base of lanthanum, barium, strontium, manganite compound are the least studied compound compared to the lanthanum, barium, calcium, mangan oxide, or lanthanum, calcium, strontium, mangan oxide. And the second one, there are only a few studies which have been conducted to understand the magnetocaloric properties of potassium substitute in LMO-based compound. So with this novelty, we try to explore this system. Next, please. And our research purpose in this system is to explore magnetocaloric effect, and the base of the magnetocaloric effect is the critical behavior. What is the critical behavior? The critical behavior is exploration after, at, and below the critical temperature or Curie temperature. So we explore above Curie temperature, at Curie temperature, and below Curie temperature behavior. And also we make some of the magnetoresistance measurement and also electron spin resonance. And we make a limitation of our research scope with the without and with the potassium dope with the 0 and 0.05 of potassium content. Next, please. And this is the basic theory in our sample. Since our sample based on the manganese interaction, so in magnetism, there is some kind of the exchange in this system. We have double exchange and also super exchange. And in double exchange, since our sample based on the parental compound LMO, with the manganese have the manganese 3+ ion, and we combine with the barium and strontium, BMO and SMO, with the manganese 4+. So when we mix this compound, so we have the interplay role of the contribution manganese 3+ and 3+ and manganese 4+. But we don't know whether manganese 3+ or manganese 4+ that is dominant for the magnetism phenomena in this sample. So that's why we want to explore this compound. Next, please. So what factors that can affect the physical properties of this sample? We explore crystal structure, average ionic radius, cation mismatch, average grain size, and the ratio of mangan 3 plus and mangan 4 plus, and average bond, length and bond angle, and preparation method. Next, please. So this is the introduction about the magnetocaloric effect. For the magnetocaloric effect, we can get the information by direct method and indirect method. Indirect method, we make some of the experimental measurement by measure for the specific heat of the sample. This is the direct method. And another one is indirect method. In this indirect method, we measure the MH curve, magnetization process. We measure the magnetization process from 0 to up to about 7 Tesla, and we measure at some of several temperature. And what kind of temperature here? Yeah, the temperature here is about the critical behavior that I mentioned previously. Yeah, below TC, at TC, and upper of TC. That is the our measurement system. Yeah. Next, please. Okay. Yeah. Next. Okay. Yeah. Sorry, the previous one. Yeah. So yeah. For the magnetocaloric effect, we want to study the transition from one magnetic phase to another in the vicinity of the Curie temperature. That's why in our experimental measurement, we focus on the several temperature for the magnetization process. And from this, we can explore the 3 parameters: beta, gamma, and delta. Beta means the ferromagnetic behavior below TC, and the gamma, the paramagnetic behavior above TC, and delta, the magnetic behavior at TC. That is the 3 parameters that we want to deliver in this presentation. Next, please. And this is the sample preparation of our sample. We use the sol gel method. Yeah, I just introduced in very slight time. Seems the time very limited. And next, please. And this is the precursor, and we use sol gel method. Yeah, we use some of the solution and to make a gel. And after that, next, please. We make a calcination and sintering process after the sample is pellet, to become a bulk material. Yeah. Next, please. And this is our analysis. Yeah. In analysis of the properties of our sample, we have 2 measure of the physical content, and the first one is structural and chemical determination, and the second one is magnetic properties. For the first stage, I would like to give an analysis about the structural and chemical determination. In this structural and chemical determination, we will give some of the experimental measurement by using XRD, SEM, EDX, and also XPS measurement. Yeah. Next, please. So in the structure analysis, we use the X-ray diffractometer, and from the XRD result, both our sample without and with the doping of potassium, we have a single phase sample, without any detectable impurities. And the second one, potassium substitution does not change the crystal structure. So the potassium substitution does not change the crystal structure, and the crystal structure is in rhombohedral, and space group is R3C. And then the crystal structure are proven from the splitting of highest diffraction peak, and from there the HKL index and Goldsmith tolerance factor, we can resolve from this kind of the result. Next, please. And this is the Rietveld refinement result. Since the crystal structure is not changed, but some of the structural parameters will slightly different. Yeah. For example, in the volume unit cell volume, in the length of the manganese oxygen length, and also the angle of MnOMn, and average crystallite size. Yeah, from this kind of calculation, we have that the crystallite size become larger if we substitute the potassium. Next, please. And this is the SEM, ADX, and elemental mapping result. From the SEM, we can see for the LKBS 0, it means non-doping of potassium, and LKBS 05, it means for the potassium doping. The potassium substitution increase the average of the grain size. We can see that the grain size become bigger, it become increase. And then from the ADS and also from the elemental mapping, we found that both samples consisted by the desired element, and potassium have axis inside the sample, for the X equal with 0.5. So this result give us the confidence about the sample, our sample. Next, please. And then XPS result spectra confirm that both sample are single phase, as is justified from the XRT. And comparison between the obtained XPS spectra and databases also confirm that the studied sample have formed a perovskite structure. Yeah, our sample is the perovskite structure, and from XPS result, we can make a justification about this structure. Next, please. And then from the XPS result, we want to pay attention about the contribution of the mangan 3+ ion and mangan 4+ ion. In the previous presentation, I emphasized that contribution of the Mn3+ and Mn4+ ion is very important in this sample, especially when we want to explore the magnetic properties. Why? Since if we see from the XPS result, we get that the potassium substitution increases the mangan 4+ ion, while reducing the mangan 3+ ion. And then what is the effect of the this condition? This will affect the double exchange interaction inside the sample. Since, as I mentioned before, the double exchange is depend on the manganese, manganese 3+ and 4+ ions, and in between there is an oxygen content. So that's why we also pay attention for the oxygen content in our sample. Next, please. In this XPS result, we get that potassium substitution increases oxygen 2- ion, from 39.14% to 41.23%. Yeah. And according to the another researcher, yeah, the increasing in oxygen 2 minus ion will result in a stronger double exchange interaction. And if double exchange interaction becomes stronger, hence it will make a strengthen in the ferromagnetic interaction in the sample. So this result will use to explore the magnetic properties of the sample. Next, please. And next, we want to analyze the magnetic properties and the magnetic properties analysis. First, we want to explore about the empty and inverse of susceptibility curve. In this curve, we have two kinds of the parameter, Curie temperature and Curie-wise temperature, and what we can get from the two from the both of the temperature. Next, please. So from the empty curve, what we find from this experimental result, yeah. First, we find the Curie temperature, yeah, and Curie temperature. We can get the Curie temperature from the first derivation of magnetization with respect to temperature. And from the figure, the inset of figure show that the Curie temperature is about 320 for the 0 potassium and 335 Kelvin for the 0.05 potassium doping. So the doping of K will increase the TC of the sample. So if we relate this empty result with the XRD analysis, in XRD analysis, we found that the substitution of potassium will increase in electronic bandwidth and manganese content. Yeah, we can see from the table, yeah, that the manganese 3+ ion from the LKBS 0 is there is a decreasing value of the contribution of manganese 3+ ion and the increasing contribution for the Mn 4+ ion. Yeah. And the same condition also can we get from another researcher, yeah, as the figure out in the figure from the Hachini, yeah, Hachini, yeah. Next, please. And from the inverse of susceptibility, yeah, we found the Curie-wise temperature. So what we can get from this Curie-wise temperature, yeah, we have that the value, yeah, of the Curie-wise temperature are larger compared to TC, yeah. For example, for the LKBS 0, TC is 320, and the Curie-wise temperature is 328. And also in LKBS 05, TC is 335, but the Curie-wise temperature is 341.6. So what is the meaning of this condition? Yeah? This indicates there are a presence of a short range ferromagnetic order above the TC. Yeah? The existence of short range ferromagnetic order can also be related to the presence of magnetic inhomogeneity. It means there is a mix, yeah, from the paramagnetic and still have the ferromagnetic order. Next, please. And then we also try to calculate, yeah, the magnetic moment of the sample as figured out in the table, yeah, for the sample. Yeah, we have differences in the value from the experimental and theoretical calculation. it can be associated with the formation of ferromagnetic cluster in the paramagnetic state, as we can get from the Curie-Weiss temperature, theta Curie-Weiss temperature. Next, please. Another magnetic properties analysis is the MH curve, and this is the main of our work here. Yeah, from this we can get the magnetocaloric effect and also critical behavior. Next, please. Yes, this is our magnetization process measurement, MH, and we see that the magnetic field from 0 to about 5 Tesla. Yeah, and we measure for about 20 or 21 several temperature, and temperature ranging from the TC and go to the upper temperature, yeah, and also to the lower of TC. Its mean is coincident is fit with the critical behavior analysis about TC and upper and lower of the TC temperature. So from this, yeah, we calculate the entropy of the system, and we see that what we can get from the entropy of the system, as I mentioned before, if without the potassium substitution, we can some of the researchers get the value of the entropy about 2.3 joule per kilogram Kelvin. And what we can get from our experimental result for the non-doping sample, our highest minus delta entropy is about 4, yeah, and 4.21, yeah. And if we substitute potassium, the minus delta entropy become larger, 4.98 joule per kilogram Kelvin. So this is our important result in the magnetocaloric effect of our sample. Besides that, we also found that our Curie temperature is 320 for the non-doping and 335 for the doping. Next, please.
Dr. Budhy?
Yes.
5 minutes left.
Okay. Right. Okay. Thank you. And from this table, yeah, what we can figure out, the important thing is if we see the TC and also the minus delta SM, yeah, we see that for the minus delta SM, our sample in this work, yeah, we have the value of minus delta SM as the biggest, yeah, 4.42 and 4.99, yeah. And if we see, yeah, for the Curie temperature, yeah, in our sample, we found that our Curie sample is more lower compared with the others, yeah, especially for the minus delta SM in the higher region, yeah. We have see that there is 311.5, yeah, but the minus delta SM is 0.74. So what we want is we want to get the sample with the minus entropy the highest, yeah, with the highest value, but the Curie temperature is approaching to the room temperature. So that is our message that I want to explore in our sample. But unfortunately, we just have 320K for our Curie temperature. Next, please. And by the critical behavior analysis, yeah, what is the message of the critical behavior analysis? We want to confirm about the ferromagnetic phase, paramagnetic phase, and the critical Curie temperature in this analysis. Next, please. Yeah. In this sample, in this analysis, what we want to get is we want to get the value of the gamma, beta, and also delta. Yeah. Okay. Since time is very short, yeah, I skip this. Next, please. Yeah. This is the determinant of order of transition. Next, please. Next, please. Yeah. Okay. Next, please. Yeah. So what we found, yeah. I'm sorry. Previously, please. Yeah. Okay. Yeah. We find the suitable model for LKBS 0.05 and also LKBS 0. Yeah. And from this we get the gamma and beta for the sample. Next, please. And we confirm the suitable model, yeah, from the previous work by using the relative slope, yeah, and we confirm that from this relative slope that the value of our gamma and beta is confirmed in this model. Next, please. Yeah. Also from here, yeah, we can find the value of beta and gamma for the LKBS 0 and LKBS 0.5. Yeah. Okay, next, please. Yeah. And we confirm what we are finding from the previous work by the KF method. Yeah. Next, please. And then we try to finding the delta value. Yeah. And we have the delta value. Yeah. Next, please. Yeah, this is the summary of the critical parameters that we can find from our sample. Yeah. Next, please. So, yeah, what we can analyze from the result, yeah, the small value of beta suggests that there is an existence of first order phase transition in both sample. Yeah, and the increase in gamma value, yeah, it means that a presence of local inhomogeneities in the sample. Inhomogeneities means near the Curie temperature, as we get from the inverse susceptibility. Yeah, we have the zeta Curie-wise, yeah, and confirm with this value. Yeah, and then we can from delta value, yeah, there is a presence of inhomogeneous magnetic state due to phase separation phenomenon or beta disorder induced by the change in manganese 3+ ion and manganese 4+ ion ratio. Yeah. Next. Okay. Next, please. Yeah. We also still confirm, yeah, our calculation with this scaling analysis. Next, please. Yeah. And correlation of magnetocaloric and the critical behavior. Yeah. Next, please. Yeah. Okay. Next, please. Okay. Yeah. So yeah. The other analysis is for the magnetoresistance. Yeah. We can see. Next, please. We found in our magnetoresistance in this experimental, we have a direct method to measure of the magnetoresistance. Indirect method is we use measurement for the resistivity versus the temperature, and after that we measure the resistivity versus temperature at the influence of the magnetic field. But in this experimental, we get the direct magnetoresistance curve. And what we found here, yeah, we show the low field magnetoresistance in our sample, yeah, and we found that the decrease in resistivity can be caused by the alignment of electron in manganese 3d orbital, yeah, thus enhancing the double exchange interaction. Yeah, as we mentioned before, that the contribution of manganese 3+ and manganese 4+ and oxygen cumene, yeah, will enhance the double exchange interaction. Next, please. Yeah, and this is the low field magnetoresistance phenomena that we can get from our sample. Yeah. Next, please. Yeah, this is the picture of the LFMR. Yeah, same as we can get from our result. Next, please. Yeah, and this is some of the experimental from the magnetoresistant phenomena, direct measurement. We try to collect the resistivity at the magnetic width 0, yeah, and we find there is a decreasing of the resistivity of the sample, yeah, by giving the potassium content, and this is confirmed with the result of the SEM experiment. Next, please. And the last is the ESR result. Yeah. So in the ESR result, that what is the important thing? The existence of paramagnetic ordering in both samples. Yeah. And then next, please. Yeah. And we can make some of the analysis, yeah, by the line width, G factor, and asymmetry factor. Yeah. Next, please. Yeah. What we can get from this, yeah, a stronger parametric interaction compared to in the LKBS 5 and LKBS 0 can be deducted from the G value in this curve. Yeah, we see that the 2.00 is the free electron G value. Yeah. Next, please. And from the line width, yeah, we can have the summary that parametric phase will broaden the first derivative of ASR signal, yeah, hence increasing the line width obtained. Next. Okay. Yeah, and then the variation of the ratio of mangan 3 plus and mangan 4 plus, yeah, also contribute to the line width of the ESR. Next, please. And the asymmetry factor, yeah, it means that the increase in asymmetry factor, yeah, due to potassium substitution indicate that the potassium substitution affect the magnetic homogeneity of the sample. Next, please. And as a conclusion, we have some of the structural analysis and the magnetic properties of the sample as I mentioned before. Thank you for this presentation.
Thank you.